Hello there, guys. Welcome to Math 115, Foundations of Mathematics 2. I'm Mike, and this is our first video for the course. In this video, we're going to get into two different types of reasoning, inductive reasoning and deductive reasoning. And these two forms of reasoning can get confused with each other. It is fairly common that people use one and they call it the other, or vice versa. So we're going to get into what these things are, what information are we using when we use these two methods of reasoning. So getting right into it, as far as inductive reasoning goes, we often use inductive reasoning to stumble upon a result which can actually be proven by using deductive reasoning later on. This is a very common thing in the world of mathematics. You stumble upon something that seems to work, you try it out a few more times and it still seems to work, so I think, hey, maybe this is a thing that's always true. And then as you move on into later math courses, if you will choose to do so, then you learn some new pieces of information that show that, oh yes, this thing that seems to be true, but I wasn't quite 100% sure, now I can be 100% sure that this thing actually is true. And the main difference between inductive reasoning and deductive reasoning is that the difference is what we're using to justify what we think something is. As we get later on into this video, we'll see what we are basing our thoughts off of, but that is the main difference between these two types of reasoning. It's what we're using to justify our thoughts and what we think is true. So, inductive reasoning is the process of arriving at a conclusion based on observations, or more commonly in the world of mathematics, of specific sample problems that we see. But the key thing to think of when you hear inductive reasoning is observations. We're coming to some conclusion based on what we see happening. The conclusion that we draw is, in the mathematics world, referred to as a conjecture. You've probably heard the word inference. That is a name that you could use as well. That's a word that we're probably more familiar with. Inductive reasoning does not prove that what you're thinking is true, although it might actually be. So if you see some pattern happening in some part of life, you may think that that is what always happens. Now, that may be true, that may be what always happens, but it also may not be true. So inductive reasoning does not prove that something is true. It does not guarantee that this is what always happens, but it just makes us think that this is indeed what happens. So a mathematical example of this here is what are the next two numbers in the sequence. You've probably seen these online, fun little puzzles just to keep your mind sharp. So I have 1, 2, 5, 26, and then two more numbers there. And sometimes these are fairly straightforward. They're pretty easy to figure out. Sometimes they're more challenging. This one is on the challenging side here. You have to figure out what are we doing to sort of go from one number to the next number in this sequence here. If I look at the first number of 1, if I were to multiply that by itself and then add 1 onto it, that gets me the next number. So, okay, let's see if that's how we get from 2 to 5. If I multiply 2 by itself I get 4, and then I add 1 onto that, I get 5. All right, so far so good. Let's try it again. Let's see if I get 26. If I multiply 5 by itself, I get 25. Add 1 onto that, I get 26. So this pattern that seems to be happening here, where I take the number, multiply it by itself, and then add 1 to get the next number, this pattern that I think we are using to get the next number in this sequence, I am coming to this conclusion using inductive reasoning. So using inductive reasoning and using what I think is going on here, I'm going to do that same thing and come up with the next 2 terms in the sequence. I'm going to multiply 26 by itself and then add 1. That's going to give me 677. And then to get the next term, 677 times itself, and then add 1 onto that. That gets me 458,330. Another sample of inductive reasoning. An example not so much mathematically geared would be, say that you watch football and you watch your favorite team. I'm going to go for the Buffalo Bills here. Insert whatever football team you want. And suppose that I've noticed that whenever a particular player is out on the field for the entire second quarter, then our team wins the game. And let's say that I've noticed this to happen over the past, say, 3 or 4 football games. Based on what I'm seeing, using inductive reasoning, we would conclude that if the team puts that particular player out on the field for the entire second quarter, no matter what game they play, then the team is going to win that game. Now, if we are realistic, does that really make sense? Is that going to be absolutely 100% true? Not really. But again, it's just what we conclude based on what we have seen. That's where you get into a little bit of the superstition of things people like to do to help their team win football games. Using inductive reasoning may require you to try a few extra test scenarios or test samples on your own and use the results from your tests to make a conjecture. So you may just be posed a question, not necessarily having seen something or worked with a particular sample. You may just be asked a question, does this fact hold? Or does this thing always hold to be true? And you may have to try some samples on your own, and then based on the results of those samples, you can make a conjecture to say, yes, this does seem to be true, or no, it's not. So here's a sample of what I'm talking about. Is the sum of 2 even numbers always even? We don't know for sure right now. Is the sum of 2 even numbers always even? So let's just try some samples here. Let's just take 2 even numbers, any 2 whatsoever. We're going to add these things up, and we're going to see if we get a number that's even. So if I take 4 and 8, those are both even numbers. Add those up, I get 12. If I take 2 and 20, they're both even. That gives me 22. That's an even number as well. And then I'll take 10 and 30. Add those up, that gives me 40. That's an even number as well. So just based on these few samples that we've done here, it does seem like this is the case. It does seem like the sum of 2 even numbers is always even. So our conjecture or our conclusion that we're going to draw is yes, we think that the sum of 2 even numbers is always even. But again, we're just drawing this conclusion based on a couple samples. We don't know for sure that this is true for all even numbers out there. If you get posed a question like that, and you come up with a sample that shows that the conjecture that you could draw is not correct, then it's called a counterexample. And here's an example of what we're talking about with a counterexample. So here is a conjecture. Someone may ask you, is a number divisible by 9 if the last two digits of that number are divisible by 9? And you may just say yes. We are going to guess that a number is divisible by 9 if the last two digits of that number are divisible by 9. So let's see if we can come up with a case where this is not true. Let's see if we can come up with a case where the last two digits of the number are divisible by 9, but the entire number itself is not. One such number that makes that the case is the number 136. The last two digits of it, 36, you can divide that by 9. You can do 36 over 9, and you get 4. But the entire number itself is not. As a quick recap, maybe going back a few years for some folks, the nice easy way that you can tell if a number is divisible by 9 is if the sum of the digits in that number is divisible by 9. So if you add up the digits in 136, you get 6 plus 3 plus 1, which is 10. 10 is not divisible by 9. And all it takes is one such test case here. All it takes is one counter example to show that a conjecture is false. What we claim to be true is actually not true. So it only takes one guy to ruin all the fun, if you will. But in order to show that there is fun happening, everybody needs to be in on it. So that was inductive reasoning. Deductive reasoning is the process of arriving at a conclusion based on known facts or statements that are known to be true. We are arriving at a conclusion based on 100% concrete knowledge, known things. So this is the difference between inductive reasoning and deductive reasoning. Inductive, based on what we see, what we think is going on. Deductive reasoning is based on what we know for sure is going on. It's based on fact. It's based on things that are known to be true. Some of us out there in the current climate are doing a lot more of inductive reasoning as opposed to deductive. Should be putting more of a focus on the deductive reasoning. Unlike inductive reasoning, deductive reasoning does indeed prove a conjecture or a conclusion. So here's an example of what we are talking about. Take a number, multiply it by 5, add 30, and then divide by 5, and then subtract the number that you started with. What is the result that you are going to get? Well, I'll tell you right now that the answer you're going to get, the answer you should get, is the number 6. But how do I know that? How do I know that I'm going to come up with 6? Well, let's do some math with this, and let's see how we come to the answer 6. So note that this statement just says take a number. It's not saying any specific number, it's any number whatsoever. So let's use some letter to stand in for the place of this number. And I'm just going to use the letter A. You could use B, C, D, E, whatever. X, you could use star, you could use cloud, whatever. But just something to stand for this number. Okay, next we are going to multiply this thing by 5. So now we're going to have 5a. We're just going to go in the order here that this thing tells us to. Now we're going to add 30. So now we have 5a plus 30. Make that a bit nicer there. Now we're going to divide this whole thing by 5. So I have 5a plus 30 divided by 5. And now, using our basic division properties and how we divide the sum of two things, this is equal to 5a over 5 plus 30 over 5, which is 6. And then 5a over 5, the 5 on the top and bottom cancel out, and that gives us a plus 6. And then last step is to subtract the number that we started with. So this is going to give us a plus 6 minus a. A minus a is 0, so we're just left with 6. So we used just basic mathematical operations: addition, multiplication, division, and subtraction here. Basic common facts, commonly done things that are known to be true. This is how we always do math. It's a fixed thing. There is no questioning that right there. So yes, this is one example of deductive reasoning, using known fixed things that are known to be true to arrive at a conclusion. So this concludes our video on inductive and deductive reasoning. In the next video, we are going to talk about estimation and being able to estimate things like costs and budgets for various real-life applications. If you have any questions or comments, be sure to reach out to me. Send me an email, send me a letter through the mail, send a carrier pigeon, whatever you have to do. Until the next video, take it easy, guys.